All right, welcome to another pre-lab video here for the Chem 1212 lab at North Georgia. This week we're going to be taking a look at the Kinetics Lab, and really it's kind of maybe a bit of a misnomer. We're really taking a look at chemical kinetics and kind of also using Microsoft Excel because we're not really going to be doing any wet lab experiments this week. We're really mainly going to be talking about kinetics and kind of some important features of experimentally, like how do we use experimental data to investigate chemical kinetics. But we're not going to be doing any new experiments this week. We're really just kind of continuing off of what we did last week and kind of using some of that data and additional data that we're going to provide to you to be able to do different calculations. So when we talk about chemical kinetics, what we're really focusing on and what we're interested in is the speed of chemical reactions, as well as what influences the speed of those reactions, like what different factors like temperature or concentrations of a reactants being the main factors that we're usually looking at. And the reason we care about finding out this information about how fast reactions happen and what controls their speed is it really just lets us help optimize reactions so that we can make reactions happen faster and maybe even potentially more efficiently. And the better we understand how a reaction works, the better we're able to do that. And kinetics also gives us a better understanding of how a reaction really takes place. And that part we'll take a look at more in the lecture portion of the class when we talk about mechanisms kind of towards the end of the kinetics chapter. Now, when we talk about kind of just general chemical kinetics, our starting point is really always talking about what we just call reaction rates. And so when we talk about reaction rates, we're looking at just changes of concentration over time. So reaction rates, we're always going to see something typically as units of molarity per second because we have a change basically in the molarity over some change in time. And so the standard units are typically going to be molarity per second. And then the next part of this that we'll typically be looking at least what we're going to be looking at kind of today, is that if we measure how concentrations change over time, we're able to now get kind of information about maybe how certain reactants can affect reaction rates and finding out something called reaction orders for reactants. This is really, really useful for us to help understand how can we make our reactions go faster if we want them to go faster, while also hopefully finding ways to help maximize the yields at the same time. But when we talk about this term reaction order for a reactant, what the reaction order is, it basically tells us, how that particular concentration of that reactant is going to affect the whole rate of the reaction. So for instance, if you take an initial concentration of some reactant and you double it, we want to know what's going to happen to the overall rate. And we'll see here in a second that usually the changes we'll see is either no change at all. If we double the concentration of the reactant, it might double the rate of the whole reaction. Or if we double the reactant concentration, we might quadruple the rate of the reaction, are probably the three most common outcomes that we'll typically see. There are some other ones. For the purpose of the lab, we're not really going to consider the other options. We're mainly just going to be looking at the main three reaction orders that we'll be talking about here in a moment. But again, we're looking at this because in order for us to optimize a reaction, we really want to understand what reactant do we need to really control the concentration of to help keep that reaction rate as fast as possible without having other kind of weird side reactions or things like that happen that are going to mess up our purity. Now, I mentioned we have our three common reaction orders, and we refer to these typically as zeroth, first, and second order reactions, or refer to reactants as being zeroth, first, or second order. If something is a zeroth order reactant, it basically means that as you change the reactant concentration, the rate doesn't change at all. The chemical rate is completely unaffected by the concentration of the reactant that we're changing. And so that means that you can change its concentration, it's not going to affect the rate at all, which means you can have its concentration be really low and it won't affect anything, in terms of kind of an optimization standpoint. You don't have to worry about having a high concentration to keep the rate going really fast. If something is a first order reaction, what that means is that for the particular reactant that's first order, that means as you affect that concentration of that compound, you're going to see pretty much the same change to the overall rate. So for instance, if you double the concentration of a reactant, the rate should also double. If you triple its concentration, the rate should also triple. If you have it, the rate should have. And so you should see kind of that consistent change between the concentration and the rate in terms of how much you're kind of altering things. And then for a second order reaction, these are the ones that are kind of the most extremely affected by changes in reactant concentration. Because here what happens is the rate of the reaction itself is actually going to change by the square of whatever we're doing to our reactant. So for instance, if we double the concentration of our initial reactant, we're actually going to quadruple the overall rate of our reaction in this case. If we were to triple the concentration, then we'd have our rate go up by a factor of 9. So we get a much bigger impact as far as what happens to the rate of our reaction if we have a reactant that's second order. So again, we can kind of quickly see here why, if we're trying to optimize a reaction, we want to know, well, which reactant has the highest reaction order, because that's the one that has the biggest impact on how fast the reaction goes. If we have a reaction between two different reactants, and one reactant is 0th order and one is second, well, we can, if the goal is just to make the reaction go very quickly, we can add a bunch of that reaction or a bunch of reactant for that second order compound, and we're going to have a much faster reaction rate as a result. And so those are things that allow us to, again, just kind of optimize reactions for things like speed. Now, there is the kind of efficiency and purity side of things for trying to get like the highest percent yield possible with the most pure product that also is considered in those processes for optimization. Those are kind of other factors. They're a little bit separate from just kinetics itself, which is really just mainly the speed. All right, now for these reaction orders, like how do we figure out, is a particular reactant going to be 0th, 1st, or 2nd order for a particular reaction? Unfortunately, we can't just look at a reaction and immediately know this information. In fact, it doesn't even match the stoichiometry of the reaction. We have to look at experimental data to really figure this information out. And so we have two common ways that this is typically done. The first, and the way that we're going to take a look at things in lab this week, is that we're going to be looking at concentration versus time data. So what we can look at is the concentration versus time data, and this will actually basically give us the information we want in terms of, is it 1st, 2nd, or 0th order. And we can do this with making plots, and kind of a variety of different plots that I'll show in the next couple slides, and comparing to try and see, well, which one best matches what we'd expect for like a 0th or 1st or 2nd order reaction, like which one does our reaction seem to fit best. And then if we want to use more kind of quantitative data as well and do kind of more calculations, we can use initial rates of reactions based on starting reactant concentrations. And this is kind of the comparisons I was saying before, where if you double one of the reactants' initial concentrations and then look at the rate, if the rate also doubles, that means it should be 1st order for that reactant. That type of comparison is really kind of this method. And you'll often hear it referred to as the method of initial rates for determining reaction order for a reaction, but it still uses experimental data to be able to do that. And so to look at kind of some of the images for what we'll actually be focusing on this week, as I mentioned, we're mainly going to be looking at concentration versus time data. And so our concentration versus time data, which you should really have this information already from last week, is if we look at concentration versus time data, we should see different looking plots whether a reaction is 0th, 1st, or 2nd order. If we have a 0th order reaction, concentration versus time data should give us basically a linear plot that's constantly decreasing in concentration over time. And it should be just perfectly linear if it's a 0th order reaction. Now, in a perfect world, our reaction from last week is not 0th order, but I do know a number of you probably saw this kind of plot on your data from last week. Don't panic if that's the case. That's not that big a deal. It's kind of our first time doing that portion of the experiment here for 12-12, so we're trying to figure out maybe what caused that for some groups. I know some of the last groups on Tuesday in particular, I think we might have had some issues with their sodium hydroxide that might have caused things to look like this, when unfortunately hopefully our plots from last week look closer to what we see over here for 1st order. And so for 1st order reactions, as we look at them, what should be happening is our concentration is decreasing as time passes, but eventually the concentration starts decreasing at a slower rate. And so we actually see kind of the change in concentration is slowing down over time. And then for like a 2nd order reaction, what happens is, we said this is the one that impacts reaction rate the most. Well, what it's actually going to cause to happen is the reaction will go really, really fast to start. So we get a really steep decrease in concentration right off the bat, and then it very quickly kind of flattens out. And so it slows down a lot over time. That's kind of the general effect. And so when I'm thinking about these different reaction orders and kind of like what they mean, or kind of looking at these concentration versus time plots, 0th order, constant change in concentration. It means it's a perfectly linear line that we can get a slope for. If we have a 1st order reaction, we are going to see that our reaction rate kind of slowly starts decreasing over time. And so we see a bit of a curve, and then we get a very kind of extreme steep curve for the 2nd order one in comparison. Because our reaction rate's much faster at the start and then slows down much quicker or in an earlier time in comparison. Now, if we're trying to compare, like, if we just plot concentration versus time, I think 0th order is easy to differentiate from 1st and 2nd, but these two are kind of hard to just look at each other and know is that 1st or 2nd order. So thankfully, we do have a good way to try and do that, and that's by looking at what kind of plots will actually give a linear line for these different reaction orders. And for 0th order, it is just concentration versus time, the exact same thing we just saw. But for a 1st order reaction, if we actually want a linear line, to relate concentration and time, what we actually want to plot is the natural log of concentration versus time. And if we plot natural log of concentration versus time, we should actually now get a linear line. And it turns out the slope of that line is actually related to our rate constant, K, that we'll be talking about here in just a moment. We see that here is zeroth order reaction as well. We also see K involved here. The slope of here also is negative K, or negative the rate constant. And so we have ways to get rate constant information from these plots also, which is another thing that's actually pretty useful to us. And then if we have a second order reaction, what's going to be different? Instead of doing natural log or just plain concentration, here we're going to take 1 over the concentration versus time. This should also give us a linear plot. It's actually only going to give us a positive slope typically, or really always. And for this, we'll see that the slope of this line actually just equals K for each for this particular reaction order for second order. And for all of these, though, again, the big idea here is if we take the data that we have, so like for instance, if you have all your concentration versus time data from last week's experiment, you can plot just concentration versus time and look, is it linear? Then take the natural log of the concentration versus time, look at that plot, like does that look linear? Then take 1 over the concentration versus time, make that plot, see if it's linear. And if you're having a hard time seeing which one looks like it's the best linear fit, just plot a linear regression line for each of them, get an equation and an R squared value, and look at which one has the best R squared value, or the R squared value that's closest to 1, because that means that's the one that's the most accurate or the best fit to your data. And so now you have kind of a more definitive way to really look at and compare, all right, for the data you have, is it closest to 0th order, first order, or second? And again, in a perfect world, hopefully from what we did last week, if you plot natural log of concentration versus time, hopefully that comes out linear or as the best linear fit. If that doesn't, again, don't worry about that. It's kind of some of the things we're really just wanting to see from you guys to see how that experiment from last week really worked for everybody. All right, now there's only one other kind of really background topic piece I'm going to talk about here for the pre-lab video. That's going to be on the Arrhenius equation. And so the other kind of factor besides just looking at what affects reaction rates or what reaction orders different reactants are for reaction, the other big thing we're going to focus on in this lab is looking at temperature impact on rate. And so rate constants themselves, which are related to how fast a reaction takes place, are going to be really affected by temperature pretty heavily. And how they are related to temperature is through the Arrhenius equation, which the 1-point form is shown here. So this is K, our rate constant, is equal to our frequency factor, basically times e to the negative EA over RT power, where for our pieces up here, this negative EA, this is what we call activation energy. And then R is our RDO gas constant, T is temperature in Kelvin. And that these pieces here, like frequency factor, this is actually just kind of a constant value that's specific to the reaction. And it actually deals with the fact that for any chemical reaction that takes place, when particles hit each other, it's not enough for them just to hit each other. They have to hit each other with the right orientation for the reaction to actually occur. And so that's what the A kind of basically correlates to, is what are kind of the needs from the orientation standpoint. Like, can these two molecules collide in almost any orientation the reaction occur, or does it have to be a very specific one that's going to affect kind of the value we see for that frequency factor? And then the activation energy is the energy that it takes for the reaction really to occur. All reactions are going to have this kind of activation energy barrier that basically has to be overcome. And once that energy barrier is overcome, then the reaction will take place. But the bigger that activation energy is, that's the thing that's really going to affect how fast reactions happen. Really big activation energies, like if we're looking at our equation here, if this number is really, really big, since it's e to the negative of this power, like the bigger this number gets, the smaller our rate constant gets. The smaller the rate constant gets, we're going to see that our reactions get slower. So bigger activation energies, so like the harder it is to kind of get over our initial starting hump for a reaction to take place, the slower our reactions are going to be as a result. And it's important to note that it's the activation energy that really affects the speed of reactions, and not just like the enthalpy change that we've often talked about for reactions in the past. And to give kind of a visual of this, so here we see like an actual image as far as like a reaction if we imagine one taking place. If we start out with just reactants and we want to eventually make products, in order for our reactants to become products, it doesn't just go straight to products typically. What's going to happen is that our reactants are going to interact in some way. They make this really what we call a high energy transition state, which is kind of it's an intermediate to an extent, that we're making this kind of new species as far as how things are combined or interacting with each other, but it's not really stable yet, and it's going to undergo a little bit more change in order to make our products. And to make this high energy transition state, since it's at a higher energy always than our reactants, that energy difference between the transition state and our reactants is always going to be then our activation energy. That's the energy that the reaction has to have in order to occur in the first place to eventually make our products. So even if in reactions exothermic, like we're getting energy back from the reaction occurring, it's still not going to happen unless we overcome that activation energy barrier first. And in terms of using our Arrhenius equation from that last slide, one of the things that we're able to do is if we want to know what this activation energy is, one of the really effective ways for calculating it is if we're able to determine the rate constant at a bunch of different temperatures, we can plot the natural log of K versus 1 over temperature. If you imagine just 1 over temperature being here, or like the X value in like a Y equals MX plus B type equation, we can make this plot, and it should be a linear line. Where the slope of that best fit line, if 1 over t is basically our x, natural log of k is our y in that case, then negative EA over r is the slope of our best fit line. And now we have a way to actually calculate then the activation energy for that reaction. This is actually a pretty common way to try and find activation energies for a lot of different reactions, because kinetic data is usually not that hard to measure, because you can just measure it over time. Just going to do it through a few trials and pretty quickly find out information about the rate constant. And then if you just do that at a few different temperatures, now you have a way to figure out effectively, or at least approximate, what is the activation energy for a reaction. Now, for the lecture portion of the class, you'll also probably be using the 2-point form of the Arrhenius equation pretty often. And this equation should look pretty familiar. It looks a lot like the Clapeyron equation from class before. Our difference here, our K's are our rate constants, activation energy here instead of enthalpy of vaporization. R is still the same, and like our temperatures and stuff are still the same. So equation format should look very, very similar, just rate constants instead of vapor pressure, activation energy instead of enthalpy of vaporization. Those are kind of the big changes that we can see. And what we end up doing then with this equation is that we use this to really go through and figure out, all right, either find the activation energy if we know rate constants at different temperatures, or if we know the activation energy, we can now predict the rate constant at some temperature if we know the rate constant at another temperature, for instance. Or if we want a particular rate constant and we know the activation energy and we know the rate constant at one temperature, we can figure out at what temperature would we get a particular rate constant if we want to really control the speed of our reactions. And so all of these are different kind of things that we can figure out simply by having kind of this type of data to be able to relate like rate constants, temperature, and activation energy. So I think this is actually kind of the end of the main pieces as far as kind of the background things we need to talk about for this week's lab. Probably the only other things I think you probably want to recognize, rate laws in general. I haven't gone over them too much here, mainly because I think you're seeing them a lot in lecture right now. I know from Dr. Foley and myself, for those of you in the lecture courses, and you're going to see them. That's one of the first things we'll talk about as we go over some pre-lab things and we start our discussions on kinetics this week in the lab. Because since this is a dry lab, I don't want to have another like 45-minute video going over every last detail, because we're going to be doing that in the lab itself already, is going over a lot of things just kind of discussion based, and really kind of walking you through some different ways to use Excel as well. So if you're not familiar with Excel, hopefully this next week will also be productive for that. But as you're going through the lab, do try hard to kind of think about, for each of the parts of the lab, like what are we really kind of focusing on information-wise from a kinetic standpoint, but then also like from the Excel side on a whole, hopefully trying to kind of learn how to use Excel a little bit better to make it easier to be able to do calculations using Excel, because Excel is a really powerful tool. And so last week's kind of final plot for trying to make a concentration versus time plot should have given some introduction to those things. We'll be walking you through some of those a little bit better this week too, and hopefully that will actually help you before that Beer's Law plot is due. So if you haven't figured that out quite yet, what you see in lab this week will hopefully help with that and make that process a little bit easier.